Dr. Zand has 20 years of experience in geotechnical engineering and geohazard assessment. He's worked with pipeline operators who face many different geohazards. His experience includes monitoring for oil and gas transport pipelines and facility piping. He's created solutions for numerous pipelines that were subject to vibration and cyclic loading from blast and construction. He holds a position at RSI Pipeline Solutions and has served as an instructor for the rock mechanics course at Ohio State University. Dr. Zand currently leads a broad range of courses on behalf of Technical Toolboxes, which you can find on our website. So our goal today is an overview of blasting and how that impacts your pipeline. Of course, there's more detailed information that you can gather through various channels after this webinar. The discussion about blasting is vital because ground vibrations and stresses from many different operations are very likely to encroach on pipeline right-of-ways. These include construction, mining, and quarrying. Occasionally, new pipeline construction requires blasting, and existing pipelines require protection from it. Blasting is not something that you encounter every day, but as a pipeline engineer, you may pass through your career without ever having to address such a situation. If you do address it, you have to get the calculations right. Determining ground strain for pipelines in the intended blast area and all of the associated safety parameters is vital to safety and uninterrupted production. So before we get into it, we're going to take a quick poll. And Robert, if you could launch that poll. So everybody should have a way to respond to this. So if you could take a second and click your response. Okay, we'll move on. Same thing, if you don't mind filling out your second question. I think we can move on. Next slide, please. So in this age, pipeline operators face a ton of challenges. There's a forceful tension between mitigating risk and minimizing cost. Potential hazards of an oil spill or gas release could ruin a company. Not all companies in the industry could overcome an event like the Deepwater Horizon disaster or some of the high-profile pipeline disasters out in the West Coast in recent years. Midstream operators must avoid disasters. But the cost of preventing them cannot be so high as to put the company out of business itself. Therefore, engineers have to be conservative in how they calculate ground strain, which adds costs and places constraints on blasting neighbors. They must allow enough uncertainty without overstepping the bounds of cost. So without any further delay, we'll turn the floor over to Dr. Zand and learn a bit more about blasting and the effects on buried pipelines.
Yes, hello everyone, and thank you for participating in this short seminar. Now, before I start, am I audible?
Yes.
Okay, perfect. So, as mentioned a minute ago, the goal of this seminar is to provide kind of a snapshot of the courses that we offer and the tools that Technical Toolboxes offer. We have more comprehensive courses and the tools in case someone is interested, and they are you can find a list of the courses on Technical Toolboxes website. So with that, let's start with my first slide. This is more related to the outside force course that I'm an instructor of, but I included that here just because I think this is important, and it is also related to the general method on how we assess a pipeline against vibration and blast. This is a distinction between load control and displacement control condition. And I don't know if you can see my cursor, but on the screen, but yeah, okay. So on this figure, the blue arrow represents a loading condition that is displacement controlled. And the gray line, the thick gray line, that is the stress-strain behavior or the stress-strain response of pipeline material. And before yielding takes place, there is not much difference between stress load control versus displacement control. But after yielding takes place, in general speaking, pipelines are less sensitive to displacement control conditions. So displacement control condition is more desirable. Example would be differential temperature or ground movement. And this picture basically shows why when the mode of loading is displacement controlled, yielding does not necessarily lead to a quick rupture, versus when the mode is load controlled. Example of load control would be internal pressure. Yielding, the remaining capacity beyond yield is not that much. So from yield to rupture, under load control condition, you don't have that much capacity, whereas under displacement control condition, there's a large capacity from yield to the final rupture or cracking of the material. So next slide, please. Yeah, this slide is the distinction between the load versus displacement control in words. And I pretty much covered this when I was talking on the previous slide, so we can move to the next slide. Another important tool that's available through Technical Toolboxes is surface loading. Encroachment or surface loading is another fairly common situation that pipeline operators have to deal with. And there are different methods that people use. One method is API 1102. Another method for general wheel load analysis is it's a method that was developed by Bettel about 2 decades ago, which is again, it is available under Technical Toolboxes. And finally, another methodology that can be used is known as the SEPA equation or the SEPA model. And in my outside course, I cover some of it. There is a completely separate course on this particular topic, encroachment, that Technical Toolboxes offers. But what the reason surface loading relates to vibration analysis is that sometimes surface loading can also impose vibration on a pipeline. An example, a famous example, is a vibratory compactor, or in general, any equipment that crosses a pipeline and at the same time creates vibration has to be thought of as a source of vibration. So not only you have to do a surface loading analysis the normal way that you perform, but you also need to look into the operation, vibration from construction equipment. And later on, near the end of my presentation, I'm going to touch on this topic, on how to handle vibration, how to assess vibration from a construction equipment such as vibratory compactor. Next slide, please. So, blasting and construction vibration. There are two general methods to assess the effect of blasting on a buried pipeline. And again, today we are only going to talk about the buried pipeline. If the pipeline is not buried, there are other concerns when you are dealing with blasting, such as trajectories hitting the pipeline. But today we are just going to restrict the discussion on a buried pipeline. And so there are two general methods or general possibilities. Sometimes the blasting site is far away from the pipeline, but they are using a high amount of explosive charge. And despite the distance, if the amount of explosive is high enough, it can still create measurable vibration at the location of the pipe. So we are going to call it quarry blasting. That's when it's far away. On the other hand, if blasting is going to take place near the pipeline, for example, within the same right-of-way, or 30 feet or 40 feet away, we have a different set of equations and methods, which is based on Esparza's equations. And sometimes you may not, it may not be obvious. You might be somewhere in between, not too far away, but far away enough that Esparza's equations, you are not sure whether or not you can use Esparza's equation. So if you are somewhere in between and you are not sure what, you can use both methods. You can assume it's a quarry blasting, use quarry blasting equation and methods, and then you can assume that this is a closing blasting and use Esparza's and take the answer that's more conservative. So the next slide, please. This is a general overview. It's just a very quick overview on how a wave, a stress wave, can propagate through soil. There are different wave types. There is a shear wave, and there is also a compressive wave. And the picture at the top, it shows the shear wave and how it propagates. The picture in the bottom, the lower picture, that shows the compressive wave. The primary difference between them is the direction of the particle movement versus the direction of the propagation. With shear waves, the direction of the particle movement, as you can see in the picture here, it's up and down. But the direction of the propagation is from left to right, right? So the direction of the wave propagation is perpendicular to the direction of the particle movement. In a compressive wave, the direction of the particle movement and the direction of the soil, the wave propagation are in the same direction. They are the same. These are called body waves, the two pictures that you see here on this slide. There are other type of waves that are called surface wave. The famous one is the Rayleigh wave. And for pipeline, it's usually the Rayleigh wave that creates the stress in a pipe. That's a surface wave. A surface wave comes into existence when you have a shear wave and a compressive wave that hit a free surface. That's why it's called a surface wave. And it's very similar to the waves on an ocean surface. There is another type of wave that's less common. It's called the love wave. It happens during earthquakes sometimes under certain conditions, but that's less common. And then aside from this type of waves, if the soil is saturated, we get another wave, the fifth type. Reason for that is because when the soil is saturated, you have two waves. One wave propagates through the solid structure, the soil skeleton, right? Then there is another compressive wave that propagates through the water, through the liquid phase, right? So you have two different phase or set of waves in a saturated medium. But again, because we are focused mainly on the pipelines, at the cover depth of a pipeline, soil is usually not saturated. And we don't have to worry too much about that. Just keep in mind that the saturated soil can pass the wave, the vibration energy better than a soil that's not saturated. Also keep in mind that a competent soil or a solid bedrock can pass the vibration energy far better than a weak soil, right? So here is a situation where a weak soil is actually better than a strong soil, because a strong soil can pass the energy from vibration to a long distance, whereas vibration energy in a weak soil tends to attenuate fairly quickly. Next slide, please. And the next slide shows you basically what is the primary mechanism of stress creation in a buried pipeline. When a wave interacts with a pipeline, a buried pipeline, there are different movements in the pipe. There is a longitudinal bending, there is an axial stress, there is a hoop stress. All those stresses actually get generated in a pipe. But the primary stress is the ring stress, is a through thickness bending. And the picture here shows the figure that I have here schematically shows the mechanism. Here, the gray circle is the pipe, intact pipe. The green circle shows the deformed shape of the pipe after vibration affects the pipe. And this type of movement creates through thickness bending in the hoop direction, circumferential direction. Now, we also get a through thickness bending in the longitudinal direction because pipe is a continuous structure. And in most cases, the amount of longitudinal and circumferential stresses are equal, almost equal, right? The equations that we have, they predict both. So for the calculations, whatever stress you calculate for the circumferential direction of the pipe due to vibration, you can assume that the longitudinal is the same. Next slide, please. Okay, so finally, this is the equation that we use for close-in blasting. Esparza's equation that I mentioned. And this is the equation for a point source. Point source means that there is only one blast hole, right? The explosive is at one location only. There are situations where you are dealing with a grip, more than one blast hole at the time. And if the time interval between two blast events is more than 8 milliseconds, you can assume that each blast is going to affect the pipeline separately. So you don't have to look into the cumulative effect of them, right? So 8 milliseconds is the key time interval to remember. If the delay between individual explosions is less than 8 milliseconds, then you have to look into the cumulative effect. If it's more than 8 milliseconds, you don't have to worry about the cumulative effect. So what we have in this equation, in Esparza's equation, are the input parameters, basically. It's the first input parameter, which is WE, that is the amount of energy that's released due to the explosion, the blast event. Other parameters that we have in the equation is the density of the soil or the rock. We have CP, C sub P is the P wave velocity in the soil or the rock. This is how fast a wave moves in the rock or soil. And this is a number that you usually have to get from your geotechnical people when you're using these equations. There are some tables in rock mechanic books that you can find some typical values. That's another approach. But usually that's a parameter that could be a little challenging to figure out. It's not readily available. R is the standoff distance. That's the distance from the point source to the nearest location on the pipe. And the P naught is the atmospheric pressure. Depending on what unit system you use, it could be different, but that is the atmospheric pressure. So let's move to the next slide, please. The previous equation, the output from the previous equation was the peak particle velocity or the radial velocity. They are almost equal. Peak particle velocity is the parameter that blast contractors usually understand and deal with. For example, they say the peak particle velocity near a structure should be less than 2 inches per second, right? That's a famous criteria that they use. Sometimes they say 1 inch per second if you're in a city. If you are near a architectural monument, they say it's ½ inch per second because older monuments and the structures are more sensitive to cracking. All those limits, when they say 2 inch per second, 1 inch per second, ½ inch per second, those are meant for either for plaster or for architectural elements like masonry or brick. Pipe is much stronger than plaster, right? So that's it should be obvious that for pipe we need to have a different limit. And the question is, how do we determine that limit? The answer is the equation that you see on this slide. This equation gives you the amount of stress from a blast operation. This is the amount of stress in a pipe from the blast operation. And so using this equation, if you know the amount of explosive and the standoff distance from the pipe, you can use this equation to calculate the stress in the pipe. And the blast-induced or vibration-induced stress plus the operating stresses in the pipe should be within the allowable limits, right? So if you know the allowable limit for your pipeline, using this equation, you can come up with a criteria for what is the maximum amount of explosive charge that can go off, that can get exploded at a given distance from your pipeline. If the stress is not acceptable, you either have to increase the distance or reduce the amount of explosive, right? When you're using this equation to exist in the pipe, the stress is internal pressure of the pipe, which usually is calculated from Barlow's equation, right? It's pressure times the diameter of the pipe divided by 2 times wall thickness. Another source for stress is the differential temperature. Sometimes people forget to account for it, but that's important. Differential temperature is longitudinal, is usually in the axial direction of the pipe. And you have to account for both. Now, we also have a table here on the right side of the slide. What that table gives you is the N factor. Because different types of explosives have different amount of energy per mass. For example, if you have 1 pound of dynamite versus 1 pound of HBX, they produce different amount of heat. So to normalize them, people have came up with an N factor. N is equal to 1 for ANFO 94.6, right? So all the other explosives relative to ANFO either have more or less energy. When they get exploded, they release either a little bit more or a little bit less energy. And that N factor is used to normalize all the different type of explosives. So the equation that we have here is for NFO. And then the N factor is included in the equation to account for different type of explosives. When you know the type of explosive, you can use this table to find the N factor and use it in the equation. Or if you are using Technical Toolboxes calculator, there is a drop-down menu that you can open the drop-down menu and pick the type of explosive, and it will automatically populate the N value for you. And if you don't like the N value, you can manually change it. Okay, next slide, please. So that was the situation where we only had one point source. There are equations for line source as well. And I'm not going to go through them because they are similar. But Esparza and his colleagues, when they developed, when they did their research program to come up with the equations, they did the testing and experiments for point source and for line source and a grid source. The example that you see here, it shows a line source that makes an angle with respect to the pipeline. And this slide basically explains different parameters, geometrical parameters that defines the line source, right? We have an angle, the angle between the line and the pipeline. We have a distance from the center of the geometry of the line source to the pipeline, and so forth. There is a spacing between the blast holes, the total number of blast holes. Just remember, again, that 8 milliseconds, keep that in mind. If the time interval, if the delay between the explosions is more than 8 milliseconds, you can use the point source. You don't have to use the line source, right? This line source is used only if the time interval is less than 8 milliseconds. All right, next slide, please. And similarly, there are other situations. There could be a grid instead of a line. Here I have given an example. You see a grid that's parallel to the pipeline. And now we have more parameters here to define the grid. We have the distance between the rows, distance between the columns, number of rows, number of columns, and of course the amount of explosive in each hole. And again, the slide shows different parameters that are used to define the geometry. There is a methodology that was developed by Esparza that allows you to analyze a situation like this as well. And technical toolboxes, if you're a user of the technical toolboxes, it does this type of calculations for you. You just have to pick the right option from the drop-down menu when you log in to your Technical Toolboxes account, or if you're using the desktop version of the tool. You just have to pick the correct option, and the input parameters are as described here. And you can use the input parameters and run the analysis. So next slide, please. So this is the most complex situation. This is where when you have a grid, and the grid makes an angle with respect to the pipeline. And the analysis method for a grid, angle grid or a parallel grid, is similar to a line source. Basically, the equations that we use for a parallel for a grid are similar to the equations that we use for a line source. And the way it works is we take the first line, the line that's closest to the pipeline. And if there is a criteria, when that criteria is met, only the first line is used in the calculations and the rest of the grid is ignored. The tests that the Esparza experimental program that Esparza performed showed that it's always the first line that dominates the pipeline when the grid is close to the pipeline. Now, if the grid is a little further away from the pipeline, then we can treat the whole thing as one single point. There is no need to think about it as a grid. We can just assume that the entire grid shrinks at the center of the geometry, which I have shown here with the orange cross. And you can use the line source equation. Again, in technical toolboxes, there is a tool that you can use for this type of analysis as well. But if you like to do it manually, the equations to use is either the line source equation or the point source equation. So we don't have extra equations, even though the geometry is more complex here. Depending on the distance from the center of geometry of the grid to the pipeline, we either use the line source equation or we use the point source equations. Next slide, please. And this is a screenshot of the tool that I mentioned under technical toolboxes. You can see just here on this screenshot, I have demonstrated different options for the analysis. We have the single point, we have parallel line, we have angled line, we have parallel grid or an angled grid. And these are the 5 different situations that I explained. So let's go to the next slide. Okay, now this slide shows how we deal with vibration from construction equipment, right? What I explained was vibration from blast operation. If we are dealing with a construction equipment, let's say a vibrator compactor, for example, or a trencher, there are different methods to calculate the peak particle velocity at the pipe. But the methods, all the methods are similar in a sense that they used a parameter that's called scaled distance. The scaled distance increases linearly with distance from the source to the pipe, right? So that's a measure of the distance from the source to the pipe, and it's normalized by the amount of energy. That's why it's called scaled distance. Depending on the scale distance, if you know the type of the equipment, you can calculate the scale distance. And there are charts like this that gives you the peak particle velocity. Here I have provided one example. There are similar charts that you can find in the literature. Also, there is a publication, there is a report published by Caltrans, California Transportation. And they have equations that are based on similar charts. So let's go to the next slide. Okay, so I think that was my last slide. I'm gonna hand it to Drew from here on.
Thank you, Dr. Zand. We're going to open it up for questions. If anybody has any questions about the content that Dr. Zand just presented, please feel free to type them into the chat or the interface, and we'll have somebody feeding those questions to get answered. While we wait for a few questions to come in, got a little marketing blurb that we're obliged to present here. And the latest generation of our tools built into the Pipeline Hub, and that's an integrated data environment that magnifies the capabilities of some of the things that have been talked about here today. We are an authorized PRCI software reseller, and we've developed a suite of power tools that enhance the user experience over the original software from PRCI. This helps maximize the productivity and efficiency of pipeline engineers. Technical Toolboxes is a thought leader and a knowledge resource provider, and we offer live and online training for PDH credits for pipeline engineers. If anybody has any questions about that, we'd be happy to answer those as well. So we provide the calculation tools to perform blast assessment as part of the Pipeline Toolbox. And Pipeline Toolbox is on the hub, and it has tools for calculating blast effects for both gas and liquid pipes. These include tensile stress strain curves, surface loading, span analysis, blasting vibrations, and many other aspects of a pipeline's life cycle. Next slide. So when we think about the current market conditions and the crunch that the oil and gas industry is under due to the pandemic and various things, key oil and gas industry metrics are at 10-year lows. The midstream sector faces the challenge of losses due to coronavirus, and it's sure to pass eventually, but questions remain as to the shape of the post-pandemic world and what changes will live on in the industry. Oil and gas companies keep moving and changing as gas replaces coal, and uncertainty creates volatile prices. The potential for market collapse means only the most efficient and productive players are likely to survive. So digital tools and effective means of knowledge transfer are essential components that will enable pipeline engineers to work most efficiently and productively. Next slide. So we want to do one more quick poll here. And Robert, if you could. So if you wouldn't mind, let us know what other technical concepts would you like to have covered in another free webinar? I think we can move on to the next. So now I'd like to open it up for Q&A. So this question comes from Ben on the line. It says, at times my group needs to use different types of blasting calculations for various projects. Where can I access or take advantage of these calculations for a gas or liquid pipeline in the Technical Toolboxes software? So quick answer to that is if you are looking for a cloud solution, we have that, and you can go to pipelineengineeringsoftware.com, register, and get access that way. If you'd like a desktop installation, you can reach out to us on our website at technicaltoolboxes.com and request access that way. I have another question from Roger. It says, I'm interested in receiving more information on pipeline blasting after the webinar. Is there more information that can be provided, or can I see some example analyses? So right after the Q&A, we're going to give a few options for path forward, but a quick answer is that we do have online resources that you can use. You could also attend a full course by Dr. Zand on blasting, and of course you can access our software from our website. So I have another question here from Jason. And it says, could a demo of your pipeline software be provided at some point to illustrate what Dr. Zand explained today? Of course, we'd be happy to do that if anybody's interested, and you can send us an email at info@technicaltoolboxes.com, or you can go to our website and request a demo from our website. Okay, if there's more questions coming in, my stream here is lagging behind. We'll have a few more minutes for questions and answers in a couple of seconds. Let's go to the next slide. So as I said, we had this slide in advance of getting that question there from the audience, but ways to continue the conversation on blasting. We're going to be releasing a copy of an ebook that has the content of today's webinar. You could get a demo or a software trial. You could go to a training course or webinar that Dr. Zand is the instructor for, and those can range from a couple hours to a whole day. Or you could go to our webpage and send us a question via that method.
Hey, Benjamin, we've gotten a lot of questions thus far on what is the applicability for pipeline toolbox blasting calculations for not only steel, but either polyethylene or plastic pipe. I mean, the questions kind of vary, but I mean, overarching, are these applicable to steel pipelines? What options exist for high density polyethylene gas lines, plastic, whatever it may be? If you would be able to elaborate on a question like that.
Yes. So to my knowledge, the equations that Esparza or other folks published in the literature, all those equations, they mainly apply to steel pipelines. If you have a plastic pipeline, you can still use Esparza's equation, but you have to be careful. Now, the reason I'm saying you might be able to use Esparza because one of the input parameters in Esparza's equation is actually the elastic modulus of the pipe. There is another factor, which is the thickness of the pipe. But there is also a range of applicability, right? So not every elastic modulus is going to be acceptable, because if the elastic modulus is too different than that of steel, the structure of steel, then it may fall outside of the validity range domain of the equation. To be honest, I get this equation a lot, and I'm intending to do a little research to see if I can find a better answer. Like there could be some specific equations that people have developed for HDPE or other type of pipelines under buried condition. I'm not aware of it, but there could be. And that is something that I can look into. But at the moment, the best answer that I have is Esparza's equations are for steel or for some material that has a Young modulus close to steel, not too different. Also, one more thing to keep in mind is because plastic material, generally speaking, they don't pass waves as good as steel. The wave propagation velocity in plastic is much lower than that in a structural steel. They are less sensitive to vibration as a general principle, general rule. So if you have a steel pipe, especially a steel pipe with a weld, that is a bigger concern than the plastic pipe when you're dealing with vibration.
Gotcha. Appreciate that. I've seen some other questions. This is just kind of in general. When will Mr. Benjamin Zand be doing, some more in-depth trainings via? We're doing a lot of our trainings for everyone via live webinar. The easiest way to go and access when it's be available or when Benjamin's doing his next course is just merely going to our website at technicaltoolboxes.com. Some of the different courses that Benjamin teaches, I believe he has one coming up for a pipeline geohazard assessment course coming up. I think it says August 18th. Looks like it's a one-day live course. He has others available as well. You might even be able to expand upon that, Benjamin, different courses you teach. But there was various questions on when are the next ones you're teaching and what all do you teach. So best way to see that is to go to our website. And you'll see a lot of different courses on there outside of blasting, but the ones that Benjamin teaches are on there. For you, Benjamin, it looks like there might have been a couple of questions in regards to soil conditions and the effects that it plays on blasting. And if you know off the top of your head within Pipeline Toolbox or the Hub, how do you enter the soil conditions for a blasting calculation?
Yes, so for the blasting calculation, the soil condition plays a role implicitly. If you remember in the equation, we had a parameter, actually we had two parameters. We had the density of the soil, and then we also had another parameter, which was the P-wave velocity in the soil. Those two account for the condition of the soil. Now, if you're wondering why there are only two parameters, for example, how comes the friction angle of the soil doesn't play a role, or the cohesion doesn't play a role? The reason for that is because the type of vibration that we are dealing with is usually a low amplitude vibration, and the soil remains in the plastic domain, right? So what's important then is going to be the elastic properties of the soil, which is characterized by density. That accounts for the inertial portion, and also the elastic modulus itself, which is accounted for by including the wave velocity in the equation. Again, if from vibration, the theory of vibration, wave propagation velocity is proportional to the square root of the modulus, right? So the soil modulus is included, and the density is included. That accounts for the condition of the soil.
Gotcha. I was talking about it for everyone, the different trainings that Benjamin teaches, through Technical Toolboxes. I mentioned his geohazard assessment one. There is another one that's a little earlier, coming up on I think it's August 12th, 13th, and maybe 18th. It's outside forces and how it affects evaluations on buried pipelines. Like I mentioned, there's also the pipeline geohazard assessment, which all of those are instructed by Dr. Benjamin Zand. Again, you can find out more information on that from our website, but the professional development hours are received on those, and Benjamin will be teaching them in their various times. The blasting specifically is on the 13th, and there are 3 webinars coming up in July. We're already in July. In August again, you can find more information on that via our website. So hopefully that clarifies some of the questions there on the courses that Benjamin is teaching. had a couple questions for you, Benjamin, in regards to kind of, again, pipeline toolbox or on the hub, anything such as vibration effects or any tools in regards to the vibration effects to that can be used for landslides, and how to determine the potential damage to the pipeline via a landslide.
So with the landslide, usually the type of analysis is different. Now, when you say vibration from the landslide, my interpretation is the pipeline is not within the landslide itself, but is some distance away. And if that's the case, let's say there is a landslide somewhere and the pipeline is 500 feet away from the landslide. So the landslide is not going to affect the pipeline directly, but it's going to cause vibration, and the vibration can cause or affect the pipeline. That is going to be similar to an earthquake, or how earthquake affects the pipeline. A short answer is it's usually not a big deal, because pipelines are very resistant against the earthquake. But if you're still concerned, there are ways to handle that. To look into the effect of earthquake on a buried or above ground pipeline. Now, on the other hand, if the pipeline is within the landslide itself, then that's going to be a ground movement problem. And how we handle that, my preference is to run finite element analysis because it's more accurate. If the amount of movement is limited, if we are talking about few feet of movement, there are methods to do the calculations manually in a spreadsheet. And you know, unfortunately, there is no easy way to give you a full answer in a few minutes that we have left. But if you're using finite element, the way to model is you can use soil springs, you can use beam elements for the pipe, and use spring to represent the soil. And then the one end of the soil is attached to the ground, the other end is attached to the pipe. You can move the end that's attached to the ground by a distance, 3 feet or 4 feet, or whatever, to simulate the ground movement condition. And that gives you the stress in the pipe after you solve the model. If you are doing the calculations in a spreadsheet, you have to you have to compare two profiles: the profile of the pipe before deflection and the profile of the pipe after deflection. And if this is the after the fact analysis, the profile of the pipe after deformation comes from survey, right? After you go to the site and you find that there is a ground movement, you can survey the pipe, and that gives the deflection, deformed geometry of the pipe. We also had the geometry of the pipe from the alignment sheets or from a post-construction survey. And by comparing the two profiles, it is possible to estimate the strain. Approximation elements is better.
Okay. I know we're coming up on the time limit. Questions are kind of rolling in right now, so I apologize for anyone that if we missed a question. We might have time for just a few more if they're straightforward. I think I have one for you, Benjamin. Do blasters sometimes do multiple charges in each hole? And how does the equations within Pipeline Toolbox handle this, if it can handle that?
Yes, so it's a good question. As I mentioned, if there are multiple charges with a delay between them, then you have to look at you have to ask them about the delay. If the delay per charge is more than 8 milliseconds, you can analyze them individually. So using the technical toolboxes, the correct option is going to be the point source. If the delay between charges is more than 8 milliseconds. If it is less than 8 milliseconds, then you got to use either the line source equation or the grid equation. Now, if the charges are far away at different locations around the pipe, then again you can analyze them separately, right? So the only time you use the grid source or the line source is where the charges are closely spaced and the delay between them is less than 8 milliseconds.
Okay. Appreciate that. Benjamin, I think we have time for one more question. Hopefully that clarified that question that was presented. Let's see, I apologize. I had the question pulled up and I lost, oh yeah, here we go. Is it recommended to depressurize the pipeline during blasting to increase the resistance capacity of the pipe to the outside force?
Usually it is unnecessary because, again, if you use Esparza's equation to calculate the blast-induced stress in a pipe, you will see that it's fairly low under most conditions. And
yeah.
Now this is counterintuitive, but the pressure in the pipe can actually help you a little bit because it has a tendency to stick on the pipe. So the decision to depressurize the pipeline comes down to the risk and how you assess the risk. If you have a pipeline that has other integrity issues, I don't know, corrosion, cracking, unknown condition of earth wells, and you're still concerned that something may happen during the blast operation, then it's prudent to lower the pressure because you know, the objective is to limit the consequence of the failure. So in that context, the answer could be yes, sometimes. But from integrity standpoint, the answer is usually no. You don't need to depressurize the pipe.
Okay, perfect. Appreciate that, Benjamin. We're coming up at the top of the hour here. I'm sure everyone has other things they got to get to. I'm going to hand it back over to President Julia Floor to close this out.
All right. Thanks, Joseph, for helping us through the Q&A there. Thanks to everybody for logging in. If your question did not get answered, we are going to capture all of the questions that were submitted and get each person a response. Again, if you'd like more information, please go to our website, reach out to us, and we will definitely get back with you on that. I hope that everybody gained some technical knowledge, got some clarification on some things that have been bothering them through this webinar, and we welcome your feedback on the webinar as well. And so with that, thank you, Dr. Zand. Thank you to everybody that logged in, and we'll go ahead and close this out for today.